Hello everyone, my name is David Kelly, and today I will be presenting you with a simple but powerful technique using Linux tools to benchmark network performance between two locally connected virtual machines. In this experiment, I will be using the software tool iperf3 for measurement and tcnetum commands to introduce an artificial delay and packet loss. The goal of this experiment will be to observe how these network conditions impact throughput and why that matters in real-world systems. So what is iperf3 exactly? Well, iperf3 is a popular open source tool that measures network bandwidth between two machines. It works in a client-server model. One machine runs the server and the other runs the client to send data and measure how much it gets through. It's widely used because it's lightweight, repeatable, and flexible. In my experiment, I used iperf3 to test TCP throughput across different conditions. First, with no interference, then with increasing delay and packet loss using Linux's TC commands. To conduct this experiment, I ran both Ubuntu VMs inside Oracle VirtualBox on my Windows 11 host. Each VM has two CPUs, 4 GB of RAM, and they were connected through an internal network, so no NAT or external routing got in the way. VM1 acted as the iperf3 server. VM2 ran the client. This setup gave me direct control of the virtual link between the machines, which is perfect for simulating delays or loss. To gather the information and form a comparison, I first started by running a baseline test with no delay or loss. I used ping to record the average latency and iperf3 to measure throughput. Then I introduced delay using tcnetum commands on the server's network interface. For each delay level, 10, 20, 30, 40, and 50 milliseconds, I ran the iperf3 test 10 times, recorded, and then averaged the results. After each round, I removed the shaping rule to reset the length. Similarly, I introduced packet loss using the tcnetum commands at 1%, 5%, 10%, and 25%, running iperf3 10 times, recording and averaging the results. Here we can see the initial baseline results for latency running a simple ping test in iperf3, which tested the throughput of the locally connected machines. As shown, I sent 20 ICMP echoes from the client to the server 3 times, resulting in an average of 1.71 milliseconds latency. I then sent unshaped iperf3 TCP messages at a 10-second interval 3 times as well, resulting in an average of 1.59 gigabits per second. After recording the initial baseline results, I then proceeded to shape the traffic, adding specific amounts of delay. Here we see the results of every test run at specific delay specifications and their averages. As you can plainly see, the bitrate drops dramatically from 1.59 gigabits per second or 1590 megabits per second to only 162.4 megabits per second with just a delay of 10 milliseconds. That is an incredible drop. As you can also tell, as delay times increase, the average transfer rate drops as well. Again, here are the results using delay shown as a visual graph. And once again, you can really see how adding increased latency can impact the performance on transfer rates. This is because TCP throughput depends on the bandwidth delay product. As latency increases, less data can be in flight or transmitted at once. With default buffer sizes, TCP struggles to keep the pipeline full at higher round-trip times. Moving on to our next shaping experiment involving packet loss. As you can see here, throughput dropped dramatically with just 1% loss, from 1590 megabits per second to just 1362 megabits per second. Much like we saw with the delay figures, as the percentage of loss increased, the average throughput dropped. This is due to how TCP functions, and that it interprets packet loss as congestion and slows down drastically. So even with a little bit of loss, through weak Wi-Fi or poor VPN connections, for example, it can have major impact on data transfers. Here we see a visual graph representation of how drastically packet loss can affect network data transfers. It is very evident how bitrate numbers can be affected if there is an issue within the network. The reason for this is that TCP responds to packet loss by backing off and retransmitting, so even a small amount of loss can severely affect throughput. So why are these benchmarks useful? Well, benchmarking is essential for understanding real performance, not just theoretical max speeds. Tools like iperf3 help identify how much bandwidth you're really getting and where bottlenecks or problems might be occurring. Benchmarks also help validate system changes, compare configurations, and guide performance tuning. Without this data, we're just guessing. In summary, this experiment showed how iperf3 can be an extremely helpful tool used for benchmarking network performance. As demonstrated, even introducing a slight amount of delay or packet loss, it is easy to see how throughput can be dramatically affected. So, as network administrators, we must always be vigilant of any discrepancies which might indicate a problem. Thank you so much for watching.